You know, there's this science that's literally all around us, shaping our world every single second. But most of the time, it's completely invisible. It's the hidden force that dictates our weather, keeps the blood flowing in our veins, and even holds a massive 400-ton airplane up in the sky. So, what is this powerful, unseen force?
I mean, have you ever been on a plane just staring out the window and had that moment of just, wow, how is this giant metal tube actually flying? How does something that weighs almost 1,000,000 pounds just hang out up here, defying gravity?
Okay, now let's bring it a little closer to home. Right this second, your heart is pushing blood through a network of vessels that, if you stretched it out, would be 60,000 miles long. How on earth does it manage that incredible job every single second of your life? And then think bigger. How can we even begin to predict the chaotic, swirling path of a hurricane? Or on the flip side, how do we design a submarine that can slip through the ocean completely silent and undetected? I mean, these problems sound totally unrelated, but they all share the same secret. The answer to every single one of those questions is fluid mechanics. It's the science of how fluids, things that flow, behave, whether they're sitting still or moving. And understanding it is the key to unlocking some of the most amazing puzzles in nature and engineering. So, let's get down to it. What really is a fluid? We all kind of know that liquids and gases are fluids, but what actually makes them different from a solid? Well, it all comes down to a really simple idea: how they react when you push on them. Okay, think about it like this. If you push your finger into a solid block of rubber, right? It squishes a little, it deforms, but it pushes back and it stops. Now, try pushing on the surface of water. It doesn't stop you at all. It just flows. It moves out of the way. And as long as you keep applying that force, the fluid will keep on deforming. That right there, that continuous deformation, is what makes something a fluid. Now, that sideways push we're talking about, that has a fancy name. It's called shear stress. But honestly, the best way to think about it is spreading butter on toast. That smearing force you use with a knife, that's shear stress. It's what makes the butter, which is acting just like a fluid, flow across the toast. You do this every day. But even in the world of fluids, there's a big difference between liquids and gases. You pour water into a glass, and yeah, it takes the shape of the glass, but it always forms that flat top. We call that a free surface. A gas, though, it's a totally different story. It'll just expand and expand until it's filled every single nook and cranny of the container. No free surface at all. That's just because its molecules have a lot more freedom to zip around. Okay, so now we know what a fluid is. The next step is to look at how it actually behaves when it's moving. And a fun way to think about this is that different types of flow have their own unique personalities. First up, you've got the two big ones, laminar and turbulent flow. Laminar flow is the polite, orderly one. All the fluid particles move in these smooth, neat layers. Picture honey pouring slowly out of a jar. It's beautiful and predictable. Turbulent flow, on the other hand, is its chaotic cousin. It's a complete mess of swirling eddies and random motion. Think of a raging river or the smoke coming off a campfire. And fun fact, most of the flows you see in your everyday life are actually turbulent. We can also sort flows by where they're happening. So internal flow is pretty straightforward. It's flow that's completely boxed in, like water moving through the pipes in your home. External flow is when the fluid is open on at least one side, like the wind blowing over your car. And this difference is super important for engineers because it totally changes how you think about friction. And then there's density. For most liquids, like water, you can push on them all you want and their density basically stays the same. We call that incompressible flow. But with gases, especially when they're moving really, really fast, their density can change a lot. That's called compressible flow, and it's absolutely critical for designing things like jet engines. So when does that change in density really start to matter? Well, for air, engineers have a fantastic rule of thumb, Mach 0.3. If the air is moving slower than that, which is about 225 miles per hour, you can pretty much just ignore the density changes and pretend it's incompressible. Why is that so great? Because it makes the math so much simpler. It lets you design cars and buildings without needing a supercomputer for every single calculation. Now, you have to realize we didn't figure all these rules out in a day. It's actually this incredible story of human curiosity and genius that's been unfolding for over 2,000 years. The story really starts way back in ancient Greece with Archimedes and his famous Eureka moment in the bathtub. But then it jumps forward to the 1700s when Daniel Bernoulli gave us the math that connects a fluid's speed to its pressure. Then, a century later, Osborne Reynolds figured out what makes a flow switch from smooth to chaotic. Every single one of these discoveries was like a new tool. And by 1903, the Wright brothers had the exact toolbox they needed to finally design a wing that could generate lift and achieve powered flight. It's an amazing chain of events.
All right, so that's a lot of theory. Why does any of it matter to you? Well, because this is where we see the payoff. Let's connect these ideas back to the world you actually live in. Just take your car. It's basically a fluid mechanics lab on wheels. That sleek, streamlined body, it's all about mastering external flow to reduce drag and save fuel. But at the same time, under the hood, you have this whole network of internal flows, fuel getting pumped to the engine, coolant circulating to prevent overheating. And covering the entire car is something called the no-slip condition, which just means the air right next to the car's body sticks to it because of viscosity, creating friction.
And let's go back to your body. That circulatory system is the ultimate internal flow machine. Your heart is this incredibly sophisticated pump, and it's because we understand the physics of how that blood flows that we can design things that save lives, like artificial hearts or dialysis machines that can perfectly mimic what your body does naturally. And when we zoom all the way out, you see fluid mechanics running our entire planet and powering our civilization. We call it aerodynamics when we use it to design wind turbines that capture energy from the wind. We call it meteorology when we use it to predict weather, and we call it hydrodynamics when we use it to design the hull of a ship so it can glide through the water efficiently. It's all the same science. But this science isn't just about the stuff we've already figured out. Its principles are right at the heart of how we're going to solve the biggest challenges of the future.
I think this quote from our research really just sums up the whole spirit of the field. It's this constant, exciting cycle of using what you know to help people, digging into what you don't know, and just having an absolute blast while you're doing it. So the next time you see a plane slice through the clouds, or just feel the wind on your face, take a second to think about that incredible, invisible science that's making it all happen. From modeling our climate to building artificial hearts, fluid mechanics is right there. It really just leaves you wondering, what's the next great challenge we're going to solve with it?